So, ladies and gentlemen, welcome. Now we are ready to talk about plant-wide control fundamentals. Now that we have gone over degrees of freedom, so let's get going. Some of the material may be repeated, but it's good to repeat things that are important. So let's consider a simple chemical process. You got fresh A being preheated in a feed effluent heat exchanger, then heated to the reactor temperature, and then the exothermic reaction A goes to B occurring in a CSTR. The conversion is not complete, 30, 40, 50%. So you got unreacted A and B in the reactor effluent. The reactor effluent is hot. It loses some of its heat to preheat the cold feed, and the cooled reactor effluent then goes to a distillation column that recovers pure B down the bottoms and recycles pure A up the top. The key point to be noted, you have energy recycle in the feed effluent heat exchanger and the distillate is being recycled back to the reactor, and this is a characteristic of all chemical processes. Process integration, it's called process integration, and it is good from the steady state operation point of view, from the profitability point of view, in the sense that material recycle minimizes the A consumed per kg B product. It maximizes the raw material utilization efficiency in the sense that every mole of A that you're putting in is leaving as product B. And energy recycle minimizes the steam consumed per kg B product. So it makes absolute sense to have recycle, and so chemical processes are full of recycle. In fact, I keep saying this again and again, and I'll repeat, if there was no recycle, there would be no chemical engineering. So while this is good from the steady state profitability point of view, uh, what recycle does is it creates two-way interaction, because the recycle can feed the disturbance back into the process, can feed a transient back into the process, and that makes operation and control a challenging issue, which is why plant-wide control is not very well understood by anybody, or is very often misunderstood. I won't say it's not understood by anybody. There are people who understand it quite well, but then there are people who don't, and it is not even well covered in any of the textbooks, and so we're going to spend some time doing it, because I think this is important for anybody who wishes to work in the chemical process industry. In fact, it's important for any chemical engineer. So now we have chemical processes with all these recycle loops in there, and these processes need to be operated safely, stably, and economically, and economics is typically reflected in production rate, product quality, effluent specs. These need to be met all the time. We want to operate the plant to meet the production objectives all the time, 24/7. The production objective itself can change, and then there are always these disturbances, ambient conditions, raw material quality, the sensors are biased, have noise, equipment characteristics, new heat exchanger becomes fouled up over time, ambient conditions, rainy season, winter season, day night, raw material quality, very nice crude from Saudi Arabia today, sour crude from Nigeria tomorrow, but the process has to process all of this and produce good quality gasoline, good quality diesel, good quality aviation turbine fuel, and so on and so forth. Now, safety and stability in chemical engineering is typically guaranteed if you can operate the process at steady state. And how do you get steady state? Well, all that you do in chemical engineering is write balances for material, energy, components, and the accumulation rate of that particular inventory is equal to rate in minus rate out plus the generation rate of that particular inventory. And if you want steady state, this accumulation rate term must be driven to zero, and that's exactly what a control system does. It drives the accumulation rate term to zero by manipulating one or more of the right hand side terms, either the rate in or the rate out or the generation rate or a combination of of the three. Usually you just manipulate one of the three. So that's that. So you need a plant-wide control system at the very basic level to drive accumulation of all independent inventories to zero, and when the accumulation of the independent inventories is driven to zero, then safety and stability is ensured because the process is operating at steady state. Independent is the keyword there. So that's the purpose of a regulatory control system. It drives all inventory accumulation terms to zero, and that ensures plant operation around a steady state. And once you are assured that you can drive the process to a steady state, then you start asking the next level of question: what steady state to operate at? For example, if you're riding a bicycle, you need to first learn how to balance the bicycle, and once you have mastered the art of balancing the bicycle, then you can start asking the question: what route should I take so that I reach from point A to point B in the least possible time? Okay, so once the process has been stabilized to operate around a steady state, then you start asking the questions: okay, now I can choose which steady state to operate at, and the steady state to operate at is typically chosen to maximize or minimize an economic criterion. For example, you would like to minimize expensive utility consumption per kg product produced, or you would like to maximize production, and so on and so forth. So this is how plant-wide control systems are typically implemented. At the base, you've got the control valves. These control valves are receiving set points from the regulatory control system, and the regulatory control system is receiving set points from an economic layer on top. And the purpose of the regulatory layer is ensuring steady operation which guarantees safety and stability, and the purpose of the economic layer on top is to ensure that the steady state at which you operate maximizes or minimizes, or rather optimizes, a properly chosen economic criterion. So that's the hierarchy of plant-wide control systems, and now we're going to look at specific processes, and hopefully by the time of the end of the course you'd be able to design a control system no matter how complicated a process may look like. Yeah, a plant-wide control system. Now, when you're designing a regulatory plant-wide control system, the key question is what to control. What should you control? Okay, and like we saw in degrees of freedom analysis, there exists tremendous flexibility in what to control, but purely from the regulatory perspective, purely from the perspective of ensuring that all steady state balances, all independent material and energy balances are closed, what you need to control are all independent inventories, and this is intimately linked to degrees of freedom analysis. Material inventories are typically reflected as liquid level. If you have gas inventory, that will be reflected in gas pressure. Energy inventories are typically reflected in temperature, or if you are vaporizing something, in vapor pressure. Pressure of, for example, a distillation column is an example of the vapor inventory in the column, and if the pressure is increasing, that means you need to increase the cooling to close the energy balance, and so on and so forth. Component inventories are typically reflected in composition measurements. On a distillation column, a tray temperature is an inferential measure of composition, in the sense that if the tray temperature is decreasing, what that means is the light key on that tray is increasing. So a decreasing tray temperature implies increasing light key composition in the tray. Okay, so you need a good handle over degrees of freedom, and once you understand degrees of freedom properly, it is easy enough to figure what inventories to control. Then there is always the need to set throughput or production. In fact, you set the throughput first, and around that you build the inventory control system, the inventory regulatory system that will make sure that all inventories accumulation terms are driven to zero. So these are things that you need to control purely from the regulatory perspective. We are not talking about economics right now. Then the next question that you ask is, okay, we need to control these inventories. That's clear from degrees of freedom. How tightly do these inventories need to be controlled? And tight control is not always the right answer. The tightest possible control is not always the right answer. In fact, often it is the wrong answer. So should energy inventories be tightly controlled? Usually yes, because energy inventories typically in reactors have a way, reactor runaway can happen if temperature starts to rise too much. Okay, so you need tight control of the energy inventory in a reactor. So typically energy inventories are tightly controlled. Should levels, now reflux drum level, bottom sump level, should these be tightly controlled? These are called surge levels. Well, usually the answer is no, because these surge drums have been put in there to filter out flow disturbances. So if the inlet flow changes as a step, the outlet flow should change as a smooth exponential rise, a lagged exponential rise. So if you have perfect level control, then a change in the inflow as a step. For perfect level control, the outflow would have to also be a step of the same magnitude. And then the question is, okay, then why did you put in the tank there in the first place? You might as well have had a straight pipe. So the tank has been put in there to filter out flow transients, and filtering out flow transients requires that the level be loosely controlled. All you need to ensure is that the level does not breach the high level or the low level alarm. So the control has to be tight enough to ensure that the alarm limits are not breached. Now whether the level is 50%, 60%, 70% or 40% or 30%, it doesn't really matter. Once you have figured out what to control, then the next question is what to manipulate. Well, typically if you looked at the balance, what would you manipulate? You would manipulate the largest term on the right hand side of the inventory balance for that particular inventory. This is called Richardson's rule. There can be exceptions to this. And there is always this pair close philosophy that is used. For example, if you want to control a tank level, you're going to control the tank level using its outflow or its inflow. That ensures that when you change the valve position, the flow changes immediately, and as the flow changes, the level also changes immediately. That allows tight control. So pair close results in fast open loop dynamics, and fast open loop dynamics allows for tight closed loop control should you wish to. Now the thing that I wanted to highlight here was that there's tremendous flexibility here, and this flexibility was partly seen in degrees of freedom analysis in terms of what are you specifying corresponding to those degrees of freedom. Are you specifying flows? Are you specifying flow ratios? Are you specifying temperatures, or a combination of temperatures, or a composition ratio? I don't know. So there's tremendous flexibility that exists in what you specify corresponding to the degrees of freedom. So what to control, tremendous flexibility exists here. And once you've decided what to control, what to manipulate, for example, a simple tank, you can control level this way, or you could control level that way. So there's two combinations right there. So there's a combinatorial flexibility that exists for a given set of controlled variables. What to manipulate, there is a combinatorial flexibility that exists there. The flexibility in what to control is almost infinite. You can choose from infinity what to control. What to manipulate, there is combinatorial flexibility. Combinatorial combinatorial flexibility. So the combinatorial flexibility and the choice of what to control, these two flexibilities make the plant-wide control design problem actually sort of like piecing together a puzzle. What do you want to control? No straight answers. Well, there are some straight answers, but you need to know. Okay. And once you figured out what to control and the reason why you want to control those things, then the next flexibility is what to manipulate. Control this using what? Inflow or outflow or some other flow, you know. So that flexibility is always there, and yeah, and one needs to be aware that we need to use this flexibility in a manner that ensures robust closure of material and energy balances, that also ensures good economics. So now let's continue. And just to show you this combinatorial flexibility, I just thought, you know, we'll take again the A to B process. We've removed the energy recycle loop here. I'm setting the production at the fresh feed. The fresh feed is flow controlled. On the reactor, the energy balance is closed by maintaining a reactor temperature, and the reactor temperature is maintained by adjusting the cooling water or the cooling rate. The reactor material balance is closed by manipulating the reactor outflow. So the reactor level is controlled by manipulating the reactor outflow. On the column, you've got the top level controller, the bottom level controller, and the pressure controller. And then you also have the reflux in ratio with the feed, and you maintain a sensitive stripping tray temperature for maintaining the purity of the product, inferentially maintaining the purity of the product, and that's your control system. One thing that I wanted to point out was that this is the throughput manipulator. If you want to increase production or reduce production, this is the set point that you would change, and this is called the throughput manipulator. All other controllers are closing some kind of balance. So this guy is closing energy balance on the reactor. This guy is closing material balance on the reactor. This guy is closing material balance on the reboiler. This guy is closing material balance on the condenser reflux drum combination. This guy is closing the energy balance on the column. This guy is closing the component balance, the leakage of the light key down the bottoms, leakage of A down the bottoms, that balance is being closed by this guy. This guy is closing the leakage of the heavy key up the top. You see, other than the throughput manipulator, all other controllers are closing some kind of balance, either a material balance, an energy balance, or a component balance. That's one point that I wanted to make. Continuing, is this the only control structure that's possible? No, there are many combinations. And the combinatorial flexibility is what I was wanting to show you. Yeah, that's the throughput manipulator. I could, for example, instead of holding the fresh feed, I could be holding the fresh plus recycle rate, that is the total flow to the reactor, by adjusting how much fresh feed I'm putting in. So in this case, you are holding the total flow to the reactor. Everything else is the same. So the specification set is different in only the throughput manipulator. Everything else is the same. By specification set, I mean we are specifying here F tot, T reactor, V reactor, L by F, and T column. These are the 5 steady state degrees of freedom corresponding to the control structure. In the previous case, if I go back, in this case, the only difference is instead of F tot, I am specifying fresh A feed. Everything else is the same. Yeah, we can continue. In this case, the the throughput manipulator is at the bottoms. So what we have is throughput is being set by the bottoms rate from the column. So we will call it B. Control shift. We'll call it the bottom rate B. And if we continue, so now you see the sump level cannot be controlled using the bottom flow rate because it's already paired. So what we do is we control the sump level by adjusting the inflow, and this assumes that there's not too many trays between the sump and the feed, because if there are too many trays, then the level control will be very loose and the sump can run dry or overflow. So this assumes that there's only a few trays between the feed and the bottom sump. And now this valve, and now sorry, I think I made a mistake here. This valve is no longer available for level control of the reactor, so the level control of the reactor is this way. So you see, from the throughput manipulator, the orientation of the level controllers is in the reverse direction of process flow. Everything else is the same as before. So what you have is this control structure corresponds to this set of specifications. Everything else is the same. The only difference is production is being set at bottoms rate. Okay, this will also work. You can keep going. Control. Now we have production being set at the feed to the column, and so the level control upstream of the reactor is in the reverse direction of process flow. The level is being controlled by adjusting the fresh air feed. Everything else remains the same as in the first control structure, and in this case the controlled variables are all the same except throughput is being set as at the feed to the column. We can continue. You can set production as vapor boil up into the column, and now because vapor boil up is being used for production, for fixing production, the column temperature must be controlled using the feed to the column. Level must be in the reverse direction of flow. Everything else is the same. You can go on and on and on. There's no throughput manipulator at a recycle or the distillate from the column. And I will leave the explanation to you so you can think what the hell is going on, but basically this is another control structure. So the point is, location of the throughput manipulator is a key decision for inventory management. It's a key decision in the sense that wherever you set throughput, inventory controllers downstream are in the direction of process flow, inventory controllers upstream are in the reverse direction of flow. And there are several alternative reasonable plant-wide control structures depending on where you put the throughput manipulator. Which one is the best? How do you bring method to the madness? So the madness is because of two reasons. One, what to control, and two, once you decided what to control, what to manipulate. And what to manipulate is largely governed by where you are setting production. Okay, so that's the madness that we're talking about. Now, how do you address issues, or how do you address this madness? I refer to it as the transformation of variability perspective, and I'll explain to you what it is and then we'll carry on from there. Very simple example, a process heat exchanger which uses steam for heating a process stream from an inlet temperature to an outlet temperature. The process stream flow can change, the process stream inlet temperature can change. Uh, if you have open loop operation, that means no control. In that case, the steam flow will be fixed. Because the steam flow is fixed, the temperature of the stream that is leaving the heat exchanger, the process stream leaving the heat exchanger, the process outlet stream temperature will show variability. It will go all over the place because process stream flow rate itself is changing, because the process stream inlet temperature is changing, and so on and so forth, because of disturbances. You say, okay, this variability in the temperature is not acceptable because maybe this temperature, this hot stream is going into a reactor, and if the reactor temperature varies so much, that's not good for conversion selectivity or the catalyst, and so on and so forth. So we don't want variability in the temperature, and to eliminate this variability, what you do is you install a temperature controller. So there's the temperature controller right there. This temperature controller manipulates the steam valve. Now if the temperature controller is properly tuned, what will happen is you will get reasonably tight control of the temperature. So the temperature variability will go down. So the temperature variability has gone down. And in order to reduce that temperature variability, the steam flow is going all over the place. So in a sense, what your temperature controller is doing is transforming variability from where it is not desirable. It's transforming variability from where it is not desirable to where it is acceptable. Yeah. So that's the transformation of variability perspective. That's one way of looking at control systems. And this perspective is what has helped me figure out the plant-wide control problem to a large extent. And I got this perspective from my PhD advisor long time ago. And finally, I do understand now what he was trying to convey. So a control system is an agent for transformation or management of process variability. So the key question that you always ask is, where can we transform process variability? Where is variability acceptable? So surge levels, like we talked about, this does not affect the steady state, so it has no economic effect. We want to regulate it loosely for filtering out flow transients, and loosely enough so that the flow transients are filtered out while the flow transients are filtered out while the high alarm and high and low alarms are not breached. Those limits are not hit. So variability in surge level is acceptable. Energy inventories, usually these are regulated tightly to guarantee safety because you want to avoid reactor runaway and things like that. Product quality, also it's usually regulated very tightly because you want to minimize free product giveaway. So for example, if you have 99% pure product, you want to sell 99% pure product, 1% impurity should be there. If you are selling 99.9% pure product, then that's essentially free product giveaway. Yeah. And mind you, the premium that you can charge as the quality improves is exponential. It's not linear. So 99% causes X. 99.5 will cost, let us say, X plus delta X. 99.9 will not be X plus 2 delta X. It's going to be, exponentially more. So the premium as the product quality improves that you can charge to the customer grows exponentially as the quality is controlled tighter and tighter and tighter. Production rate, often loose is okay. For example, a plant will have a monthly target. Your target, the business side will say, okay, this plant, our analysis of demand supply gap says that we can sell so much, and so your target for this month is produce so many tons of the product. So you have a monthly target. So on a daily operation basis, you don't have to operate on target on all 30 days of the month. On some days you can be high, on some days you could be low, on some days you could be where you need to be, and so some variability in the production rate is okay. Production rate needs to be controlled, but often lose control of production rate is just fine. What about recycle loop circulation rates, or the recycle rates? Usually these need to be regulated tightly, and if the recycle rate variability is well regulated, then the recycle rate doesn't swing as much. If the recycle rate doesn't swing as much, all equipment in the recycle loop sees relatively fixed flows, and that's good for all the equipment inside the recycle loop. However, one needs to be careful in the sense that we may need to let the recycle rate float in order for the overall balance on a plant to close. And I'll just give you a very quick example. The quick example is as follows. I mean, it's the same example as the process, but I'll just draw it here for convenience. So you've got this process, and let's say you're flow controlling the feed to the process. In this case, the recycle will have to be allowed to float. Why? Because the overall material balance is K times XA times V. We are assuming, first order reaction kinetics, and that's the generation rate of B in the reactor. And this should, and let's assume that the product is pure. So product rate is P, should be equal to P, which should be equal to FA. You see, now if you increase FA, temperature is fixed, volume is fixed, so K and V are fixed. Do you see that XA has to increase to close this balance? If XA has to increase, this composition is fixed. The only way XA, the generation rate is, what it is. So P moles per hour of C will be produced in the reactor. B will be produced in the reactor. So the A composition must go up. The only way it can go up is for the recycle to increase. So the recycle must float to the appropriate value so that this balance can close. Okay, so that's what I mean when I say that we may need to let the recycle float for overall balance closure. Now let's look at a common energy recycle loop. So what we have here is, we've got feed at temperature T0. क्या हो गया यार ये? Okay. We've got feed at temperature T0 coming in. Let's say the reactor effluent is hot. So the hot effluent gives some heat to the cold feed. Cold feed gets heated, and then it gets further heated to the reactor inlet temperature in a heater. The hot feed after cooling goes to a cooler, and everything condenses. The condensate is taken out as liquid. That's the process. Now let us say we are running the process. Without any temperature control. So basically the firing rate is fixed. If the firing rate is fixed, that means the energy input is fixed. Then let's say the temperature of the in stream goes up. Also the assumption is that the reactor single pass conversion is not large, maybe 30, 40, 50%, but certainly not 90, 95%. So low or moderate single pass reactor conversion. So there's enough unreacted reactant in the exit stream of the reactor. So let's say the inlet temperature goes up. If the inlet temperature goes up, this temperature will go up. If this temperature goes up, you're putting in the same amount of heat, this temperature goes up. If this temperature goes up, the reaction rate will be exponentially faster. So this temperature will go up quite a lot because there's a lot of unreacted reactant. The reactor conversion is not 100%, it's 30, 40, 50%, it's low or intermediate. If this temperature goes up, more energy gets transferred here, then this temperature goes up, then this temperature goes up, this temperature goes up further. So you see, the reactor temperature will actually tend to blow up. And the thing that this reveals about the process is, for variability into the recycle loop of the energy, as the energy input, enthalpy input into the recycle loop changes, with this scheme of operating things, the energy or the temperature inside the recycle loops, they keep increasing. Now imagine what we do now is, so the nature of the process is, if the feed temperature increases, all temperatures in the recycle loop will increase a lot. Where will they settle at? They will settle at 100% conversion, whatever the temperature is corresponding to 100% conversion in the reactor. Yeah, because then you have no more fuel left to burn. Okay, but if you operate the process like this, all temperatures will go up. Now let us say what you do is, you say, okay, now we'll manipulate the heater duty in order to hold the reactor inlet temperature constant. Now in this case what happens is, if the temperature goes up, if the inlet temperature goes up, this temperature goes up, this temperature goes up, and if this temperature controller is tightly controlled, it will reduce the energy input so that this temperature which had gone up goes back down, and therefore this temperature will stay pretty much constant. It won't go as much up. It'll go up a little bit, but then it'll come back because the inlet temperature has been brought back. You see, so what is happening here is, the action of the temperature controller, the reactor inlet temperature controller, is transforming the energy balance variability out of the recycle loop, and this will stabilize the process. So the temperature controller transforms energy balance variability out of the recycle loop, and this actually regulates the amount of energy or the rate of energy transfer in the feed effluent heat exchanger. When you did not have the temperature controller on, when it was on manual, the energy transferred in the feed effluent heat exchanger went up and up and up and up. That's called a reactor runaway. Okay, but if you control the reactor inlet temperature, reactor runaway won't happen. I think it's easy enough to see that it doesn't really matter, as long as you control some temperature in the recycle loop, the runaway will be prevented. Yeah, so that's the key message from this very simple example. You want to transform the variability out of the recycle loop. That's the message. Now here's another way of doing it, and I think I won't go over it. Let it be. Material recycle snowball effect. So you see, in most systems, the reactor is quite expensive because the catalyst is very expensive, and so the design will have a small reactor volume, a low single pass conversion, and if you have a low single pass conversion, the recycle rate would be high, and if the recycle rate is high, what you find is, if you increase the feed rate 5%, the recycle rate doesn't go up 5%, recycle rate increases, I don't know, maybe 20%. So the gain or the sensitivity of recycle rate to production rate changes is actually quite high. This is called the material recycle snowball effect, and it's figuratively. So if you're doing this where you're fixing the fresh feed, those are the set points that affect the steady state, then a small change in the fresh feed rate will cause a very large change in the recycle rate. This is called the snowball effect. Okay, so right now we are saying we're showing pure A. I mean, it could be that A contains a solvent and the composition of A in that fresh feed goes down or up. What that means is, if the amount of fresh air that you're putting in varies, the recycle rate will vary a lot. And if the recycle rate varies a lot, all the equipment in the recycle loop will experience large changes in flow, and that's not good. In fact, very likely the column may flood, and if it's a sieve tray column, it may weep. So you will start hitting operational constraints. Equipment will start hitting operational constraints because the recycle rate is showing large swings. So because recycle loop shows large swings, let us say the management asks us, okay, maximize production. But I am the operator of the process, and I know if I make a small change in the fresh air rate, recycle can show a very large swing. And I don't want a large swing to occur, and I'm scared that such large swings may upset the column, will cause the column to flood, and so on and so forth. What will be my response to the management? Will say, well, this is the maximum production, because I don't want to take that risk of large swings in the recycle loop and some equipment in the recycle loop then acting up and saying that, look, oh, I have exceeded, I have hit an operational constraint, maximum level, minimum level, or one of the valves is closed or fully open, or the column is flooded or weeping, and so on and so forth. So because of this large tendency of the process to show large swings in the recycle rate, even though the process is capable of higher throughputs, you would be running at a low throughput, and therefore your derating from the maximum possible throughput that the process is capable of delivering is actually large. Now let's look at an alternative structure, and let's go. Okay. Everything is, all the other loops are the same except for that brown loop over there. Instead of holding the fresh A feed, now what we are doing is we are holding the total flow to the reactor by manipulating the fresh feed. So you see, the fresh feed is being brought in as a makeup stream. Now imagine the same disturbance, the concentration of the fresh A feed changes. If the concentration changes, recycle rate will change a lot. If the recycle rate changes a lot, the total flow to the reactor will change. That change will be detected, and the flow controller, the throughput manipulator flow controller, will either increase or decrease the fresh air feed rate so that the total flow to the reactor remains fixed. So you see, in this case the recycle is fixed and variability is there in the fresh feed. In the previous case, the fresh feed is fixed and there is variability in the recycle loop, in the recycle rate. In this case, what's flowing through the recycle loop is fixed because this is fixed. Because this is fixed, what's going around the recycle loop is by and large fixed, and variability is there in the fresh air feed. On the other hand, if you looked at the previous, in this case, this flow, control. In this case, the fresh feed is fixed. Recycle flow or total flow to the reactor is going all over the place. It's showing large swings. Okay. So let us say you are operating the process with this control structure where the total flow to the reactor is fixed and the fresh A feed is being brought in as a makeup stream in order to hold the total flow to the reactor fixed. In this case, even though the nature of the process is such that if there is variability in the fresh air feed rate, if there is variability in the composition of the fresh air stream, then the recycle will show large swings. In this case, the action of the throughput manipulator is such that it transforms variability in the recycle rate out of the recycle loop. That being the case, now let us say the management, same management with this control structure, comes to the operator and says crank up production. Now you see, I can crank it up gently. I can crank this up, the total flow rate set point, gently, and take it close to whichever is the unit that hits a maximum limit. So let us say the column flooding is the unit that hits maximum limit, and variability in the column vapor rate is this much. You see, now I can take this with confidence because the recycle flow is reasonably fixed. On the other hand, if I had the previous control structure, then the variability in the column boil up would have been much more, because not only is it rejecting other disturbances, it is also rejecting disturbances due to large changes in the feed flow to the column. Right now, in the black case, the variability in the feed flow to the column is much less. Because the variability in the feed flow to the column is much less, the variability in the boil up is much less. Because the variability in the boil up is much less, I can get closer to the flooding limit of the column, which is that max. Yeah, so in this case, there are no large swings in the recycle rate, and therefore the throughput derating would be lower than the previous case. Yeah. The key guideline that emerges from both these examples is that you want to structure the control system to transform variability out of the recycle loop. How do you do that? You do that by holding what's going around the recycle loop constant. In an energy recycle loop, you hold a temperature inside the recycle loop. In a material recycle loop, you hold the component rate going around the recycle loop. And the material balance control structure will then bring in the fresh component which are recycled as makeup streams. If a component is not recycled, then there is no problem because there is no recycle of that component. That particular component, you can have flow control of the fresh feed. But if you are putting in a fresh feed and that component is being recycled, then you should hold a flow in that recycle loop so that the fresh feed of that component is brought in as a makeup stream. That's the key guideline that emerges from recycle loops from these very simple arguments. And with that, I think I'll end this lecture. I don't know how long it has been. We will further discuss what happens in snowball. We will further discuss the snowball effect in the next lecture and see further reasons as to why it is recycle rate that should be held constant and not the fresh feed. Okay, that's that. So let's thank you for your attention and we'll call it quits now. I don't know how long it has been. About a 50-minute lecture, 48-minute lecture, so that's reasonably okay. Thank you very much and goodbye.